Now let us turn our attention to the design of the resonator network. At oscillation, we will have this condition. At least for stable single frequency oscillation, the conductance looking into the active device, GD, will be equal to the negative of the conductance of the resonator, GR. As well, the susceptance of the device will be equal to the negative of the susceptance of the resonator. We're going to concentrate on the reflection coefficient looking into the resonator network and making sure that reflection coefficient has the behavior that we need for stable single frequency oscillation. The design of the resonator network must follow the Kurokawa condition for stable single frequency oscillation. This is rather a long expression, and when we're doing design at a gigahertz and above, one of the strategies followed is to simplify that expression. So the simplified expression here is simply saying that the derivative of the drain conductance with respect to voltage times the derivative of the resonator susceptance with respect to frequency must be greater than 0. Comparing the simplified expression with the full Kurokawa condition, we need to set the second term in the full condition equal to 0. We're going to be closer to 0 if we achieve these two approximations. We would like the derivative of the drain susceptance with respect to voltage to be approximately 0, and we would like the derivative of GR with respect to frequency equal to 0. These are the conditions that come from the Kurokawa condition, but we have some other requirements as well. So first of all, look at this requirement. This requirement here says that we want BD and BR to be independent of amplitude. The frequency of oscillation is largely determined when BR is equal to minus BD. We want to design our oscillator so only the susceptance determines our oscillation frequency and the conductances determine the amplitude of the oscillation. If we ensure that BD and BR are independent of amplitude, then we will keep phase noise as low as we possibly can. Any white noise that appears on the amplitude would translate into a frequency dithering if BR and BD were not independent of amplitude. Another condition we want is to achieve a GR that's independent of amplitude. And of course GD must change with amplitude so that oscillation builds up and saturates, and at oscillation we have this condition here where minus GD is equal to GR. Most oscillators using transistors are most conveniently designed to be conductance oscillators, and GD just falls off with amplitude. So GD dV is positive. GD itself is becoming less negative, and so dGD dV is positive. And if we look at the simplified Kurokawa condition, this condition here, we see that if GD dV is positive, then dBr d omega must be positive. That is, the derivative of the susceptance with respect to frequency must be positive. So we want to achieve many of these things simultaneously. So the resonator network cannot be too complex to achieve all of these characteristics simultaneously. Grouping these characteristics together, these are the properties we want to achieve with our resonator network. Now it is one thing to look at these in terms of the derivative of the susceptance and the derivative of the resonator conductance and to look at the rectangular plot, but with some experience we would like to look at these conditions on a Smith chart. One of the reasons for this is that we become very comfortable with the Smith chart in design. As well, when we're going to realize this oscillator, we will have to do design using CAD tools and we will have to do measurements, and the measurements we would like to represent on a Smith chart, and we want to compare those measurements to what we were thinking of during the design process. Now those conditions on the left half of that slide can be represented on the Smith chart. We need a reflection coefficient of the resonator network, gamma R to rotate clockwise here, and the direction is in the direction of increasing frequency. So susceptance is negative above this line, it's negative up there, it is positive below the line. Now one of our other conditions is that we want the conductance of the resonator network with respect to frequency to be equal to 0. That is, gamma R must follow a line of constant conductance, as shown here. Furthermore, we want GR and BR to be independent of amplitude. So we want no dependence on the amplitude. So if we did a measurement and we changed the amplitude of the signal that is driving our resonator network, we do not want gamma R to move from that line. We do not want it to be dependent on amplitude. During the design of the resonator network using CAD tools, we can test this as well. We can drive the resonator network with an active port, change the available power from that active port, and see if gamma R will change with amplitude. Now you may be thinking that we're going to design a resonator network that is passive. How could the amplitude change? However, we're designing a voltage-controlled oscillator. We must have an element in there that we can vary. We're going to vary the capacitance in our resonator network by using Varactor diodes. Changing the bias on the Varactor diodes will change the capacitance of the diode and hence change the resonant frequency of the resonator network. However, because it must be dependent on the DC voltage, that capacitance value will also be dependent on the RF amplitude. And if there is a dependence, there is a possibility that we will have a variation of the susceptance of the resonator and the conductance of the resonator with respect to amplitude. We cannot avoid that, but we would like to keep it as low as possible. Well, one way to keep the derivative of GR with respect to amplitude small is to make sure that GR is as small as possible. When we're designing a fixed frequency oscillator, we can deal with a resonator which is using ideal components in the resonator network, or near ideal components in the resonator network. We don't have to use a reverse bias diode, but with a VCO we must. So with a fixed resonator network, we have more degrees of freedom in the design of our oscillator. Since we're dealing with a VCO with a Varactor diode, there will be finite conductance. We will not be operating our oscillator near the unit circle, especially when we're above a gigahertz or so. We will be inside. We will be in this region. And for the oscillator that we're designing in this case study, this is about where we happen to be. Now we have a way of lumping our resonator design criteria into the behavior of the reflection coefficient. There are two other characteristics that we want for our resonator. The first one is that we need to ensure oscillator startup. And in the last segment of the case study, we determined that this blue dashed region here is where we need the crossover point between gamma R and 1 over gamma D to be, at least when the signal is small. And we need that condition for the oscillator to start up. That is, we want our reflection coefficient for the resonator network to indicate that we have a capacitance looking into it, or at least a capacitive susceptance with a little bit of conductance. So we want to be in that region. The second characteristic that we need is that we need the resonator network to be tunable. And the situation we want is that when we change the voltage on our Varactor diode, we want gamma R to stay on that same fixed conductance curve, but to rotate. So we have a lot of things to achieve here. We need to be in that dashed circled region. We want gamma R to stick to that constant conductance circle no matter what frequency we're operating at and what our tuning voltages are going to be. And when we're at microwave frequencies, we really need to keep the resonator network as simple as possible if we're going to achieve all of our objectives. So we want the resonator network to be essentially a simple parallel LC circuit, and we're going to build on that and make it a little bit more complex. For example, we will replace the capacitance by a Varactor diode, and we will replace the inductance in the resonator network by a transmission line. Secondly, we want the resonator to be designed, that is LR and CR to be selected, so that we have a high derivative of the resonator susceptance with respect to frequency, and we want to control the magnitude of our oscillation. Third, we will have a conductance which will come from the inductance in the resonator network. We can reduce that conductance by replacing the resonator inductor by a transmission line, so that primarily the conductance of the resonator comes from the Varactor diode that is used to implement C. There will be a dependence of the resonator conductance and susceptance. Ideally, this would not happen, but there will be some dependence, and that dependence will come from the Varactor, because of course the Varactor must be nonlinear if we're going to apply a voltage across it to change the capacitance. And because it is a diode, it will have a finite series resistance, and that is the primary source of that conductance. A secondary source of that conductance, and it could be the major source in some situations, occurs when the Varactor conducts current. Ideally, it's a reverse bias p-n junction diode, but this Varactor diode is part of a resonator network, and there will be a large RF swing across it. And in this segment of the design, we're going to spend a little bit of time talking about what we can do to minimize the variation of GR and BR in response to an amplitude change. Of course, the amplitude change that we're really worried about is the amplitude that corresponds to noise on our oscillating signal. We do not want that noise, the white noise on our oscillating signal, to be translated to frequency noise or frequency dithering, because that results in phase noise, and phase noise is a critical characteristic of our oscillators. Here is our resonator network. On the top left there is a resonator network which is in the form of a parallel capacitance and inductance. We will apply a DC tuning voltage through an inductor which acts as an RF open circuit or an RF choke. We will have a capacitor as well, which will be an RF short circuit, but a DC block in particular. We have a capacitor between our Varactor diode and the transmission line, which replaces the resonator inductance LR, and that capacitor must be there for a DC block, but it serves another purpose as well. In fact, in good design, we really like to use an element or component of the design for multiple purposes. We're going to use that capacitor to provide a little bit of fine tuning to the resonator network. Now we have a wide microstrip transmission line here. It is going to be low impedance and it is going to have low loss. Now our Varactor diode is a special type of p-n junction diode. It's designed so that the capacitance is as linear as possible. That's the main characteristic. The capacitance of the Varactor diode will vary with the voltage across it, and eventually that capacitance becomes a very large, at what is called a built-in potential. We usually only bias the Varactor diode in that negative region, because in this positive region the capacitance is changing very quickly. We want to use the Varactor diode so that there is very little variation as the RF signal level varies. So let's look at our Varactor diode in a little bit more detail. The characteristics of that Varactor diode have a significant impact on the variation of the susceptance with respect to frequency and in our tuning range. Now we want negligible current flow because that will give us low shot noise. As well, if there is any current flow, we will have a finite conductance. And so we have a region here where there's a lot of current flow when our voltages are out here near the turn-on voltage of the diode, and when we're near the breakdown voltage, there will be a lot of current flowing in the reverse direction. Between VB and 0 volts, there is very little current flowing, typically of the order of picoamps, and we could potentially go over into this region. So this IV curve exaggerates really what is going on, but so that we can see what is happening. So if we tune the Varactor diode to this voltage, and our RF signal is fairly small, we will have a nice controlled capacitance value. I've drawn here the RF signal as a sine wave. It's centered on the DC voltage Vtune, and in this case we see that our voltage is varying and the effective capacitance value at each time point on that RF signal will change. So that if our RF signal increases in amplitude, the average value of that capacitance will vary. So the amplitude of that signal could vary because of white noise on our RF signal. That white noise will result in a small capacitance variation. That small capacitance variation changes the susceptance of the resonator network and results in phase noise. So here are some points. We choose the tuning voltage to minimize the DC current. We have to keep that DC current as small as possible so that the resonator conductance is small. So minimizing current flow minimizes GR. But if we design a good resonator, it will have a large RF voltage swing. That doesn't matter if we're using lumped elements, because we can support a fairly large RF voltage swing without any change to the capacitance or inductance values. So we're minimizing current flow, but what do we do if the RF voltage swing is too large? Recall that what we want is the derivative of BD with respect to voltage being approximately equal to 0. So let's address what we're going to do if the RF voltage swing is very large, because in fact if we have a good resonator network there will be very little loss, and if there's very little loss there will be a large RF voltage. The classic solution to the problem that we're encountering, that is with the susceptance of the resonator network being dependent on amplitude of the RF signal, is to use a Varactor stack. This design uses a 4-diode Varactor stack, but we could use many more diodes, but 4 is enough for this design. Here is the Varactor stack here. The inductors in the Varactor stack act as RF open circuits. This capacitance acts as a DC block and an RF short circuit. So if you follow the signal path here, you will see that each diode has a voltage Vtune across it. In fact, each diode is going to be reverse biased with a voltage Vtune across it. Our DC voltage is the same across each diode, but the RF signal that appears across that variable capacitance is equally divided across each of those diodes. So while with one diode we have a CV curve that looks like this, with the stack of 4 Varactor diodes, this is what our CV curve looks like on much the same scale. So we see that the capacitance has a variation with respect to voltage. Now we of course would change the size of the diodes to give us the capacitance range that we want, but we see here that the derivative of the susceptance with respect to voltage will be 1/4 with our Varactor stack as it would be with our single diode. So let me superimpose the RF signals here. You can see where the RF signal is with our single diode. There's a fairly large variation of capacitance as our RF signal changes, and that variation is much smaller when we use the Varactor stack. The Varactor stack also reduces GR and the derivative of GR with respect to voltage, that is variation of the resonator conductance with respect to amplitude. So our single diode is on the left, the 4 diode stack is on the right. Let's have a look at the IV curve. So the RF signal is redrawn here. Now with this RF signal we will see that in this region here we now have some 4 diode current, and so there will be a small finite conductance of the Varactor diode. If we go over to the IV curve for the 4 diode stack, we see in this region that the current is going to be much smaller. So GR for the 4 diode stack at the same tuning voltage will be a lot smaller. So here I've added the RF signals at another tuning voltage. So that's the red curves there. We see that when we change the tuning voltage, we move a little bit more into the reverse bias region, there will be significant current flow when our RF signal extends into that breakdown region. But when we're with the 4 diode stack, we can keep away from that breakdown region. In fact, the effective value of that breakdown region in terms of the RF voltage itself looks as though it's 4 times VB of an individual diode, because our RF signal is equally divided across each of those Varactor diodes in the stack. Another similar characteristic is the effect of the Varactor stack on the tuning range. The range of tuning voltages is essentially determined by the current flow through the diode. There is forward current flow and there is reverse current flow when we reach breakdown. So I've exaggerated things here a little bit. I've shown 2 RF signals on the IV curve. The purple RF signal and the red RF signal result in the tuning range being very narrow. That is, the legal values of tuning voltage are really quite small. If we wanted to increase the tuning range, there would be more conductance and the performance of the oscillator will reduce. And so in the CV curve we'll see that we'll be able to go from a value of capacitance here to a value of capacitance here, which is only a little bit larger. On the 4 diode stack we see that we can vary the DC tuning voltage by quite a large amount, and with the same RF voltage swing we can keep away from the reverse breakdown region and away from the forward current region, and the tuning that we can achieve of capacitance value is really quite large, much larger than we possibly would have expected by simply multiplying the tuning range by a factor of 4. Here is our final resonator. It's laid out on a printed circuit board. This circuit is good at 5 GHz. This circuit has surface mount components, and let's go through and identify all of the various components and how they relate to our schematic diagram. First of all, we have these choke inductors here. They have a fairly high impedance at our 5 GHz of oscillation, and here are the 4 choke inductors. Well, that's 3 of them, and here's our 4th one at the top here. Our Varactor stack is here. These diodes are available in surface mount form. The capacitance on the top here, which acts as a DC block, but it also provides some adjustability, are these 2 half picofarad capacitors across the top. Our wide transmission line, which we could call the transmission line resonator, but it's really part of the overall resonator, is shown there. And the connection to the active network is through that point there. And that is the gamma R that we're simulating, and it'll also be the gamma R that we measure. Other characteristics of this microwave circuit are things that you commonly see in microwave circuits. And what we have are lots of vias to ground. If there is a spare space, we will provide a via to ground. This does two things. One is that it reduces the ground resistance and ground inductance of the vias, and in addition it suppresses the spurious parallel plate modes that could possibly exist in the substrate. Let's look at this transmission line again, because it does seem a little bit strange. We have a connection to the transmission line here, we have a connection to the transmission line here, and we have several vias across the bottom, and then we have this shorting strip. So what is going on here? Well, that shorting bar corresponds to the short circuit in the schematic. What we have achieved is an adjustable length transmission line. So effectively, this looks like the short circuit line. Of course, it's not quite a short circuit across there. Maybe it's more accurate to say the short circuit looks something like this. But we need this adjustability when we're getting the oscillator to work in the lab. So each of these oscillators will require some manual adjustment. And this shorting bar is available as a 0 ohm resistor. It is a surface mount element, so it seems strange to buy a 0 ohm resistor. We can use the same equipment that places the other surface mount elements. This shorting strip going up the right here is the other connection for our shorting bar. These design features can be used in many designs. Now, if we were doing a design on an RFIC, we'd need to minimize the amount of adjustability required. But here we're building a circuit board based oscillator circuit, and we can do adjustability, and so we have a design which is fairly affordable. We see one adjustable element here, the adjustable short circuit. We can also adjust the lumped elements that we're placing in the circuit. So let's look at some of those adjustable components. First, we have our RF chokes and we have a DC block. The top two capacitors there provide a capacitance adjustment. Now we have two capacitors there. Those capacitors could have different values and give us a much wider range of adjustability. It just so happens in the final design here that they're both half a picofarad. But you could find in some designs maybe one could be 1 picofarad and one could be half a picofarad. And so we can achieve a much wider range of capacitance values and much finer adjustment as well. We need that adjustment here so that we can fine-tune the capacitance of those Varactor diodes. The availability of Varactor diodes with a particular capacitance value is much smaller than the available of lumped element capacitors. So this is a convenient way for us to achieve a fairly wide range of tunable capacitance. We have a transmission line, and that transmission line can be modeled as two lines. Now that transmission line, this wide, low impedance microstrip line, is called a tapped microstrip line. And it can be modeled as two transmission lines. So we go from point A to point B using one transmission line model. We go from point B to point C using another transmission line model. And we have a tap at point B. Now that tap transmission line provides impedance transformation. Now this microstrip line can be approximately modeled by this, but we have found in our simulation that we need to do electromagnetic analysis of that transmission line to get anywhere near the performance that we need. Now the last characteristic that we need to go over is the ability to tune the reflection coefficient of the resonator. That is, we want to change gamma R as we change the bias, and we want that gamma R to follow a very particular characteristic. Now this is an impedance Smith chart here, and you need to imagine that we have an admittance Smith chart, and these loci, there are actually two loci here of gamma R, are approximately following a line of constant conductance. Now there are two loci here. These are the loci of gamma R at two different tuning voltages. One at 1 volt, that's the black curve there, and the other curve, the red curve with the crosses on it indicating frequency, is the reflection coefficient at 3 volts. Now this is a fairly nice characteristic. This is the resonance that we're using to establish our oscillation frequency. Those resonances there, those two resonant curves are sitting on top of each other. There is an additional resonance here at lower frequency. We're trying to build an oscillator that operates between about 4.5 and 5 gigahertz, or 4 gigahertz and 5 gigahertz, in that range. And this other resonance here is at a much lower frequency. So we must make sure that our 1 over gamma D curve does not intersect with those gamma R loci at the low frequency resonance. Now, you may be thinking, where does that resonance come from? Well, our resonator network here is really quite complex. We have a tap transmission line here, we have quite a few capacitors, and that resonance does show up in simulation as well, and so it's something to do with all of those elements that we have in there. But our primary resonance has just the characteristic that we want. Now let's imagine that the crossover region between gamma R and 1 over gamma D is just this dashed blue area here. So that is where the crossover is going to be. So here we have a little dot which is on the reflection coefficient locus for a tuning voltage of 1 volt. And that dot is at 4.5 gigahertz. And when we change the tuning voltage to 3 volts, we have a cross here at 4.8 gigahertz. Yes, that dot and the cross aren't at exactly the same point, but approximately changing the tuning voltage from 1 volt to 3 volt has changed the oscillation frequency from 4.5 gigahertz to 4.8 gigahertz. Now the locus of 1 over gamma D is going to go something like this. This is eventually what we're going to see. It's going in that direction. It will vary with frequency. Ideally, it wouldn't vary with frequency, but we cannot build a microwave circuit which has an admittance that doesn't vary with frequency. We just try to minimize it often. And so we're going to have a 1 over gamma D curve that's rotating in the counterclockwise direction, and we're going to have a gamma R curve that varies in the clockwise direction, and where these cross at the same frequency will determine the oscillation frequency. And our active network we'll talk a lot about later on, but the small signal 1 over gamma D curve is out here, and it moves in that direction until we have a simultaneous intersection at the same frequency and the same amplitude. So the amplitude will be established when the negative conductance of the active device is equal to the conductance of the resonator network. Now that conductance of the active network we design so that it is independent of frequency. And so it is essential for us to have a conductance of the resonator network that is independent with frequency. Well, we're not perfect, but we are very close to being perfect. We are almost on a constant conductance curve. So let's summarize where we are. This is the resonator network. It really looks quite simple, doesn't it? There are only a few elements, and this is for a design that operates at 5 gigahertz. The transmission line was chosen to replace the inductor, mainly because it has lower loss. A lumped inductor has really quite high loss, and we really cannot get a very good lumped inductor at a high microwave frequency, or above about 5 gigahertz or so. The Varactor stack reduces the resonator conductance, and it reduces the resonator conductance by keeping the RF swing around from those current conduction regions. It keeps the RF swing away from the forward conduction region and away from reverse breakdown. The Varactor stack also reduces dependence of the resonator admittance on the signal amplitude. In this case, we have 4 diodes in our Varactor stack, and we have reduced that dependence by approximately a factor of 4. This circuit has several adjustment points. We can design our network with all of the elements in it. We can select B at the design stage, so that's a coarse adjustment. Adjustments that can be done on the lab bench as we produce each of our oscillators are at A and C. The adjustment at A requires us to change lumped surface mount capacitance values. The adjustment at C requires us to move that shorting bar or the 0 ohm resistor. So at the very final adjustment, a person working on the lab bench will have a shorting bar which they will have connected through kind of liquid solder. That shorting bar will be moved up and down to just get the finest of adjustments. Then the solder will be allowed to harden. In the next segment, we're going to talk about design of the active network.